Seated, but now I'm perfect. Oh, come on, that was a good one. No, I used to be conceited, but now I'm perfect. No, okay. You can't win them all. Right, well, what we're going to do today is look at section 2.5 on continuity. Here's a kind of basic description of what a point being continuous at x equals a is. If the overall limit exists and it's a finite number, and the overall limit is the same thing as the value of a function, then it will be a. Then it will be continuous. If either one of these two restrictions are not met, then the function is discontinuous. And last time we looked at jump discontinuity, infinite discontinuity, and removable discontinuity, which are the three major situations that you tend to get. And yesterday, didn't we talk about left continuous and right continuous as well? So what I want to do today is kind of go over some of the homework questions. It's not that we don't know how to do these questions. It's just that sometimes it's not clear what they're asking us in the question, right? It's the way it's phrased, or the particular situation might not look as clear as it could be. So that's what I want to spend a lot of time on today. And then towards the end of today, I'm then going to look at when is a function continuous? In other words, what range of values of x would a particular function be continuous? Right. So here goes. We got a chat. What's the chat? Okay, Bill. I got you. Right, and let's kick in. Now, we did use these questions, but I used them in the way I wanted to. Remember, we did these questions and we used them to identify discontinuities and jump discontinuities and removable. And I also used them for left and right continuous, right? So it was a nice picture to kind of ask you those questions. But now we're going to look at what you're really being asked in each question. So here is a pretty messed up function. You agree it's got problems in all sorts of places. And we're being asked to use this graph, find each x value where the function is discontinuous, and then to state whether it's right, left, or neither. So let's start with this one. The smallest value of x here, where the problem has where the function has a problem, is -4. Okay. Now let's look at -4. Is this function continuous on the left, continuous on the right, or it's just not? It's neither of those two. At x equals -4, continuous left, continuous right, or neither? What's going on there?
Neither.
Correct. Right. The next one would be -2. So you'd go and you put in -2. That's the next number along. And continuous on the left, continuous on the right, or neither this time?
Left.
Agreed. If you focus just on that little narrow window, right? So imagine you just looked at -2. Would you say that the left branch has a dot on it, so it's continuous on the left? You remember the solid dot thing. And so in this case, continuous on the left. So do you kind of understand what they're asking and what they're expecting from you now? That's what question 1 really was about. And then it goes on and asks you about some other ones. So this one is a little bit different, but only a little bit. It talks about a thing called a comma separated list, which I think you probably figure out. Look very carefully at this graph. Tell me the x coordinates of the discontinuous places. So what's the first one?
-2.
-2.
Agreed. They don't ask it, but isn't -2 a removable discontinuity? That would be its name if they'd asked it. Who's next?
-1.
Right. What would we describe -1 as if they'd asked it, which they didn't? We'd call it what kind of discontinuity?
Infinite discontinuity.
Yes. I'm putting the next one in. Would you agree the next one is 0 and it would be a jump discontinuity? Might as well finish it. Wouldn't 1 be the next bad guy? And do you notice a comma separated list just means you write down the numbers with commas between them. Right. So if you just wrote those numbers without the comma, it would probably say you're wrong. So you need the commas. Comma separated list. You weren't quite aware of that. Now you are. Now, this question is a similar looking graph, right? And this time it's saying, for which values of a, which is for what x coordinates, does the function approach a different number from the right as it does from the left? And here are all the places to look, and we check the ones that work. So I'm going to start with x equals -2. Would you agree that the function approaches the same value because they meet in the middle? So I'm not using that one. Why am I not picking -1? X is -1. Why am I not picking that one?
It's
Both
infinite.
negative infinity.
Yeah,
Because infinity isn't a number.
yeah. That different number is important, right? Because number means 42. Infinity is not really a number. A number is a specific value, right? So I'm reading it that way. So far, I haven't found one. So do you want to tell me one that does have a problem where the answer on the left is not the same value as it is on the right branch? Because there is 2 answers where that's true, isn't there?
Yep, 0 would be the next one.
Right, and would you all agree that at 1, the same thing is happening? Okay. Now, in this bunch, same graph, they're now interested in the values of x where the function increases or decreases without bound. God, it looks like I was a lawyer here. Do you know that just means infinite, doesn't it? I mean, they could have just said, find the value of x where g of x is infinite. I think that would have been much easier to understand, but that's how they phrase it. In which case, wouldn't we choose -1? And then it says, or when g of x is not defined. So when the function g of 2 or g of 4 or whatever it is not defined. Okay. At x equals 0, is g of 0 defined? Does it have a value?
Yes.
Yes. Isn't there I can't move this damn thing. Isn't there a dot on the left branch there? You see that solid dot? Right. How about at -2 then? Is g of -2 defined? No, so that'll be one of the ones I'll pick, right? -2. Would I pick 1? Is the function defined at 1? Does g of 1 exist? Look at the picture. Does g of 1 exist? Is it there? Yeah. It's floating in midair, but it's still there. So you go through this list and you pick, I forgot which one I said I was going to pick here, -2. And here you write down all the places where bad things happen. So you would be putting in -2, -1, and so on. So you just do one of those comma separated list things again. This is a pretty straightforward question. I think nothing too pretty straightforward again. Right, I like these questions. What you're going to be told is here's a function and it's got some things wrong with it. And then they give you 4 pictures and you pick the one that's got the same things wrong with it. So in this question here, it has an infinite discontinuity at -2, right? So doesn't that mean it's got a vertical asymptote at x equals -2? And it's got a removable discontinuity at 2. Okay, so infinite discontinuity at -2 and removable at 2. Does it look like picture 1 to you? Is it infinite at -2 and removable at x equals 2? No, it's not that one. Is it infinite at -2 and removable at 2 in the second one? Nope. How about this one? And then you go, oh. Now, isn't that going to be a really quick homework question? Because all you do is pick one with 4 pictures. And there's only one right one. So you pick it. Now, in this story, a jump discontinuity at 7 and a removable one at 5. Would you agree it's not that one? A jump discontinuity at 7 and a removable one at 5. How about that one? Is it a jump? I'll get this right. A jump at 7 and a removable at 5. Agreed? That one. There's another one. Pick one of the pictures. There's another one. Pick one of the pictures. The other class has already done this, and I'm disagreeing with the book because I'm allowed to. Doesn't mean I'm right. I'm just going to disagree with them. Here are 5, 1, 2, 3, 4, 5 situations. And it says, which of these following is a continuous function? So you imagine that you collected information on each of these stories and you graphed it. Would you get a nice smooth curve, right? No jump discontinuities, no vertical asymptotes, right? Nothing weird, just a nice smooth curve. Okay, so the temperature at a specific location as a function of time. I would go with that one. We didn't disagree with the Weber sign. The temperature at a specific time as a function of the distance west of New York. Okay, so you pick noon, and in New York, it's 29 degrees because it's winter or whatever, right? And then you go 1 mile northwest, 2 miles west, 3 miles west, 20 miles west, and that's your x-axis. And it is. And that's the only 2 answers that Webbersign wanted. And I disagree with them. I think there was others. But since I can't change any of the answers in Webbersign, will you just remember it's the top 2 and move on? Because you may well be able to say, I think the 4th one is also continuous, or I think the 5th one is continuous. So let's just pause for a minute. If the 3 that are next, do any of those 3 look to you like they should be continuous? In which case you're probably going to agree with me.
So I was thinking the taxi ticker would be continuous, but it would only be continuous if it was an analog ticker instead of a digital one.
Oh, that's been sneakily precise. And actually, I agree with you when you say it that way. Yeah, okay. So it depends, I guess, on, you know, the way the thing works, because it might click, right? 18 cents, click 19 cents, right? But it might be more digital, in which case every value could up. So we could put that one in. How about the current in a circuit for a light in a room as a function of time? Could that be continuous?
I think they were specifically mentioning it earlier in the book as being like current circuits cut dead off at certain points, which would make it sound discontinuous.
Yeah, okay. I'm going to have to accept that one then. I was thinking, you know, you switch it on, even if it's a microsecond, doesn't the power go up and then it kind of levels off? And then when you switch it off, technically when you switch something off, isn't there a microsecond where it actually loses its energy? So it's more like a very sharp hill, flatlining and a very sharp hill downhill. That's what I was imagining, that it was continuous. But if they want to argue that in a real circuit that doesn't happen, I guess they're correct.
I think how lights work is I'm pretty sure they flash 60 times a second. I'm not super smart in this area, but I think they.
Oh, because of hertz and
Right.
alternate current.
Mm-hmm.
But they flash so much you can't see them because it's so quick.
Which is why they flash on camera if you don't have the right equipment.
Ah. See the things you find out in this class that you weren't expecting to. Is that connected with sometimes when they take a camera of wheels turning, the wheels look like they're turning backwards? You know, like in a wagon wheel in a Western or something.
That's a different effect, but I don't remember the name for it.
But it's something to do with the fact that the camera is only taking, it's not a continuous process. It's taking like 60 or 100 or whatever it is, pictures a second.
Yeah,
And
and your eye
if
does the
that
same
much,
thing.
yeah.
I think our own eyes do that as well, and I think our brains literally don't move fast enough to see it going the right direction.
Well, our brains are funny things. Yeah. Okay. That was interesting. Basically, just pick the top two to keep WebAssign happy. So just remember that for question 10, or you'll be guessing forever and arguing with them. We are now going to move on to the second part of what today is about, which is I'm going to give you some notes on when is a function continuous, but we're now talking about an interval. So here's my first function. For what values of x? So it's an interval now. That's an n. Let's do polynomials. For example, x cubed minus 7x, or as another example, let's just pick x squared. If you were being asked for what range of values of x is a polynomial function continuous, the answer, and I'm going to do CTS for continuous, because I want to do it as an abbreviation, is actually every single value of x. If you think about it, aren't polynomials just wobbly curve functions? But aren't they all connected to each other? Aren't they all continuous? Would you agree? A normal polynomial function doesn't have vertical asymptotes in it, or jump discontinuities, or removable discontinuities. Isn't every polynomial in the universe continuous for every single value of x from minus infinity to plus? So the interval of continuity is that. You could call it that guy. Have you ever seen the capital R, which is short for all real numbers? You could have written it down as, in English, all real numbers. But in WebAssign, they only want the answer using what is called interval notation. So if you were being asked for what range of values of x is x cubed minus 7x continuous, there is your answer. Do you see? You don't do any math. You don't need to solve any equations. We just take it as a known, obvious piece of information. Would you agree it's obvious that polynomials are just okay? They're continuous, right? There's nothing weird going to happen. And it doesn't even matter how ugly the polynomial. Couldn't I make that 1.1 x cubed take away 3/4 x, and it would still be continuous, wouldn't it be? Easy to do. So that's the first one anyway. Now, radicals. A radical function could be something like the square root of x minus 1. A radical function could be the cube root of x minus 1, or the fourth root, or the square root of x squared minus 90, right? Radicals have square roots and cube roots and fourth roots in them, right? That's what a radical is. Now, when are they continuous? Well, that's a little bit harder, because doesn't it depend on the function what the answer is? Now, let's take the funniest one, or the strangest one. For this guy here, can you plug any value of x you like and get an answer? Yes. Can't you plug -20 and -20 billion and plus a trillion, and it works? So this one is continuous everywhere. This guy is not continuous everywhere. And you might think, I don't believe you. Well, if I sketch it, and this might help. Right, that's what the square root of x minus 1 looks like. Is this function, and it sounds like a daft question, but it's not, is this function continuous at 0? Is this function continuous at x equals 0? No, because the function isn't even there at x equals 0. You can't evaluate it. So this guy, isn't this guy only good from 1 and everything bigger? That's interval notation for x greater than or equal to 1. Do you agree? So how do we generalize all these different types of radical functions? Because there's an infinite number of them, right? You could write them all down. It's covered by this phrase. All radical functions are continuous on, oops, it's EIR, on their, on their domain. Which means if you can get an answer, it'll be continuous at that place. Are we good? Let's give you one more radical before I move on. Oh, by the way, side note, do you know cube roots are continuous everywhere? You know, as long as it's a polynomial inside. Because can't you get cube roots of negative numbers and positive numbers, so you're not going to have a problem evaluating it. Right, back to this fella. I want to know for what values of x is it continuous? That is not an easy question. So wouldn't it be nice if we could visualize it? Because if I saw a picture of it, wouldn't it be easier for me to tell when it's continuous, right? How would you sketch that guy? And don't make your life hard. Think of an easy way of doing it. Any suggestions? An easy way of sketching that.
Use Desmos?
Yeah. Use Desmos. Well, you're trying to think to yourself, maybe I'm not allowed to use Desmos. No, you're allowed to use Desmos. I mean, you can use your TI 84, but your TI 84 is not as good as Desmos, in my opinion, for a couple of reasons. Sometimes if you do functions like this in your TI 84, it ends up kind of floating in midair, and it's not always obvious, you know, where this is and this is, because it leaves a little gap because it has problems. I don't know why, but it does. So I'm setting up Desmos right now, and hopefully, no guarantees, hopefully it's going to appear on the screen momentarily. Please tell me you're seeing Desmos. Oh, good. Yesterday I had a whole load of hassle. Okay, so y equals, gotta get some space here. Y equals, I need the square root, so click this guy, and where's my square root? Is it in here? Where's the square root?
3 over from the
Oh
bottom
God,
left.
there it is. God, my eyesight. There we go, x squared. Take away 4x and make that go away. If I move this a little bit, can you see that this function exists from 0 going to the left and from 4 going to the right? You see the curve goes like this. Now that I see that, that would be negative infinity to 0 and from 4 to infinity. So let me zoom back to where we came from. Are you happy about where these two numbers came from? By the way, my picture was wrong. And that's what it looked like in real life, but I wasn't really making any attempt to draw it properly. You feel comfortable about intervals of x where a function is continuous, right? Plug it into Desmos if you're not sure what the damn thing looks like, and you should be able to answer the question just using the picture in front of you. And that takes us through 2 of the 4 situations. So polynomials are continuous everywhere, and all of them are continuous everywhere. Radical functions are continuous on their domain. So if you can draw a picture, you should be able to figure out where it exists, right, where its domain is, and you're good to go. The third one are rational functions. And they are continuous on their domain. Let's show you what that looks like. I could put that into WebAssign, but I don't need to. Would you agree this function has a problem at only one place? Right, there's only one value of x where this rational function is going to have a problem. Agreed? Where is it?
7.
So won't it be continuous for everybody except 7? Now, it's been a while since you did interval notation, but that's how it looks in interval notation. All the numbers from negative infinity up to 7, don't use 7. Join to all the numbers starting at 7, but don't use it, and finish at infinity. Can you remember doing those interval notations? Normally, didn't you do it when you were writing down the domain of a function? You might use this notation. And didn't you also use it when you were writing down the solutions to inequalities? Remember, you would use interval notation in those. So it's just a little niche market. You didn't see it a lot, but you did hopefully see it enough times to feel comfortable about it. If I did draw that, wouldn't there just be a vertical asymptote at x equals 7? Right? Now, how about this function? Don't rational functions have problems when the bottom is 0? Right? That's what causes the trouble. Now, if I need to solve this question, then is it my goal to find out when the bottom is 0? Now, I'm trying to do this algebraically rather than doing it all the time with Desmos, because we get a little bit lazy if we do it with Desmos. Plus, sometimes the factors might not be nice numbers, and you might not be able to read 7/5 easily out of Desmos. So if you just take the bottom guy and you factor it, would you agree you get that? So far, so good. Now, doesn't that tell me that there's a vertical asymptote at 8 and there's a vertical asymptote at -1? So pretty much you would have done similar things when you were doing sketching rational functions in 141. So aren't these the only two places where the function has a problem? So that means it's continuous everywhere except here and here. Now it gets a bit clunky in interval notation. So -infinity to -8, and then you go from -8. That's a plus. Let me try again. It's continuous from -infinity to -1, and then you go from -1 to 8, and then you go from 8 to infinity. That's what happens when you poke a hole in two locations. Now, you might say, why do I need that middle one? Imagine it goes like this. This is my x-axis. Isn't there going to be a hole at -1? Then there's going to be a hole at 0. So this is like that piece. This is like that. I'm going to stop for a second. Yes.
I'm a bit confused now. So wait, so if an asymptote doesn't make a function on continuous, then couldn't you say that any function is, quote, continuous on its domain, unquote? Because like if its domain is where it exists, then like it's always going to be continuous there.
You're not confused. You are saying a true statement.
So then what's the point of saying?
Well, the point is we're being asked to find when is the function continuous. And so we're doing it. The fact that that answer is the same answer as what is the domain of that function is kind of helpful, isn't it? Because if we know how you get the domain and continuous is the same interval, we kind of know the answer.
Okay, yeah. So
right?
So yeah, all functions are continuous on their domains.
Pretty much, yes.
But wait, hold on. There's a comment. Is that related to what I'm saying?
Oh, that's what I heard you say at the beginning. Well, that's what I thought I heard I said.
Oh, okay, that makes sense.
Okay, we're good. Sometimes you have to process information. I'm getting some weird feedback that is a slight distraction to me. So I'm just going to mute you all. Yeah. When you do rational functions, I think someone was mentioning removable discontinuities. Most rational functions, when the bottom is 0, you get a vertical asymptote, but you can actually get a removable discontinuity as well. It's still a discontinuity, right? The function is not. So if that's what the person was getting at, let me show you a rational function like that. Now, the bottom is 0 at 2 and -2. So that's how you would write down all the values where a function is continuous. You agree that's everything, poke a hole at -2, and this bit here, poke a hole at 2.
We can't see your paper.
Oops, I'm out. Sorry, put it back in. There we go. So if you looked at this rational function, and there's a problem at 2 and there's another problem at -2, agreed? And this is the two places where the function is discontinuous. And so it's continuous everywhere else. Now, what I was saying is that normally when you get a 0 on the bottom, you get a vertical asymptote, right? But not always. Sometimes you get a removable guy. Now, in this case here, do you see there's an x minus 2, and there's an x plus 2, and there's an x minus 2. And if you cancel these guys out, you get that. Now, that is a vertical asymptote at x equals -2. And this fella, x equals 2, is a removable discontinuity, right? So I'm going to move over and show you that one. It doesn't change the answer. The answer is still -2 and 2 are the only two bad guys you need to worry about. But what happens there might not always be a vertical asymptote. So I'm going to be putting that guy that I just mentioned. So I'll put a little bracket. That's important that you have brackets here. Okay. Now, can you see the problem at -2, the vertical asymptote? Now, okay, can you trust me that there is a removable discontinuity x equals 2? Because there really is. So I'm going to, unfortunately, Desmos does not seem to use the feature of removable discontinuities. It doesn't put a little hole with a circle, and it really should have, but well, you get what you get. This function looks something like this. There should be a hole there. Removable discontinuity. So, if you are doing a rational function and you're trying to find out when is that function continuous, you will need to find out essentially what its domain is, which really becomes find when the bottom is 0, right? And that's the bad guys, and then you got it. So let me show you a more awkward version of that.
We can't see the paper.
Thank you. There we go. Let's look at the domain of this function. Right, it's a fraction function, right? So it's a rational function, not your typical one, but it's still rational. Isn't the problem going to happen when the bottom is 0? So far, so good. Now, isn't the problem going to happen when e to the t is 1? Can I go from there? And it's pretty obvious why. Now, what value of t makes this happen?
0.
So won't our function be continuous everywhere except 0? So that's the basic process. If you have a fraction function, right, a rational function, and you're trying to find out when it's continuous, you kind of go looking for the bad guys, or in this case, bad guy, right? What makes the bottom zero? And whatever that is, and it doesn't matter if that causes a vertical asymptote, it doesn't matter if that causes a removable discontinuity, doesn't it cause a problem, and therefore it can't be used. And for our last guy, and our fourth family of functions that we're going to look at. So we've looked at polynomials, radicals, and rationals. Who do you think is my last family of functions that we're going to look at continuity of?
Trigonometric.
You're right. That's the last one. Well, this kind of brings back what Corwin was saying. Trig functions are continuous on their domain. So, if I went and said to you, where for what values of x is the sine of 2x continuous, wouldn't the answer be everywhere? Right? There's not a problem with the sine of 2x, isn't it a nice curve? Everywhere. So that one would be continuous everywhere. On the other hand, what about the tangent of x? So while you're thinking about it, doesn't the tangent of x have essentially an infinite number of problems? Agreed? Now, writing down the interval in which the tangent of x is continuous really isn't practical. Wouldn't it be 0 to pi upon 2, and then pi upon 2 to 3 pi upon 2, and then 3 pi upon 2 to 5 pi upon, I'm getting fed up, dot, dot, dot. But doesn't it also go dot, dot, dot the other way? And can you see how that is not a good notation, right? Interval notation doesn't really work. So let's just not do a tangent function in the homework, right? Let's just say, and they're not going to do it. If they wanted to, you'd have to do set builder notation. Right? If you wanted to know what that would look like, you would say it was continuous for all values of x such that x was not equal to plus or minus a half pi plus k pi. That would be one way. Right. Just start with a half pi and then add multiples of pi. Add 1, 2, 3, or take away 1, 2, 3, and that would work. Oops. Don't you get a negative answer as well as a plus as you go to the left and to the right? So trig functions are continuous on their domain. So if you can find a value for it, it'll be continuous there. If you can't find a value for a trig function, then it won't be in, that will not be in its interval here. So which functions play well and which don't? Aren't sines and cosines really nice? They play well together, right? Tan has a problem. Doesn't cotangent have a problem? Does secant x have a problem? Yeah. Doesn't secant x look like a big U and then a big upside down U, but it has a vertical asymptote at fixed places forever? And that is a perfect point for us to say we are done. So, yeah, say hi and bye-bye.